In this video, we're going to go over exponential growth and decay. Remember that you can write exponential functions in one of two ways. You can write them either as p0 b to the t for some base b, or you can read it as p0 e to the rt for some number r. Okay. Now, for the function on the left, if you write it like that, then the number b is the one you have to keep track of, right? P0, of course, is just the initial value. That's what you get when you plug in t equals 0. So t you think of as time. So at the initial time, t equals 0, you get p0. And then b is a base. It's a positive number, and it's not equal to 1. So either it's less than 1 or greater than 1. When it's less than 1, then the function looks like this, never touching the t-axis. And it hits the y-axis at the value p0. And when b is greater than 1, then it looks like this, concave up and increasing, never touching the t-axis again, and it hits the y-axis at p0. So when b is less than 1, you have exponential decay, and when b is greater than 1, you have exponential growth. Now, when you write it like the function on the right, in this purple, which I have circled in purple, it's still an exponential function, so it's going to look like one of those two that we've already drawn. But of course, which one is it going to look like depending on whether r is negative or positive. And of course, you can guess what it's going to be. When r is negative, it's going to look like this. Okay, same deal. And when r is greater than 0, it's going to look like that. Okay, hitting the y-axis at p0. All right, and so when r is less than 0, that's when you have decay. And when r is greater than 0, that's when you have growth. Now there's a simple reason for that, and it has to do with the fact, first of all, that e is about 2.718. So when r is less than 0, you're essentially e to the r, you're essentially taking the reciprocal of e, so that's going to be a number that's definitely less than 1. So the base is less than 1, that's why you're going to get this graph. But when r is positive, you take a number that's greater than 1, you raise it to a positive power, that's still going to be greater than 1. So that is why we get growth. All right. So those are the two kinds of exponential functions. That's how you can tell whether or not you have decay and growth, depending on how in each case. And there's a reason why we actually study this function more than we study the other function, and it's because of that number r, which, if you recall from the interest rate problems, remember you saw this when you had interest rate problems where the interest was getting compounded continuously, that r represented the nominal interest rate. But in general, it actually represents the relative growth rate, relative rate of change. Okay, relative rate of change. And of course, when r is positive, then you have relative, it represents the relative growth rate. And when r is negative, it represents the relative decay rate. Okay, so that's what's special about that function on the right, the e to the rt type exponential function. It's because that number r represents the relative rate of change, which is an important quantity you'll see over and over again in the class. So, next thing I want to do though is explain how those two kinds of functions are related. And it turns out that you can always express one in terms to look like the other one. So in other words, if you start out with b to the t, then you can actually make it look like e to the rt. And it's really simple. You're just going to use basic or elementary rules of exponents and logs. So you have p of t equals 10 times 2 to the t. Initial value is 10, and the base is 2. So 2 to the t. You want to write it as e to the rt. So look at this, how I'm going to do it. 2, just using rules of logs, is equal to e to the ln 2. Okay? But we're raising that to the t power. So this is actually equal to 10 times e to the ln 2, just separating it from t times t. And so what is the r? It's just ln 2. Okay? So r is just equal to ln 2. In other words, if you have an exponential function b to the t, then the relative rate of change for that exponential function will just be ln of the base. okay? ln of the base, in this case it's ln2. All right, now let's go to e to the rt. If you start out with that function, so in other words, they give you the relative rate of change. In this case, it's just the number 2. That's the relative rate of change. And you want to write it as just a standard exponential function, some base to the power t. So how are we going to do that? Well, we'll do that. There we go. E to the 2t is equal to 10 times e squared to the power t. All right, that's just a simple exponents rule. If you have something raised to an exponent, you raise it to another exponent, then the exponents multiply. And that's all I've done. So that's the only rule I've used there. So that's equal to 10 times whatever e squared is. All right, what is e squared? That's going to be our base. Okay, so that's equal to 10 times b to the t, whatever that number e squared is the b. All right, so that's how you can get from one to the other. And when you look at functions e to the rt, that r is special, and it's what we know is the relative rate of change for that exponential function.